Welcome back. We're going to be continuing on the eigenvalue and eigenvector train and exploring eigenspaces today. But to start off, we're going to be looking at a joke. So let me tell you this one. What do you call a baby eigensheep? A lamb, duh. Get it? Haha. So we don't want our lambdas and eigensheep just running all amok, so we need a space to enclose them. So basically an eigenspace is a way of enclosing all of our eigenvectors and their corresponding eigenvalues to a little space that is a subspace of our vector space. We're going to have some matrix A, which is this matrix here. We're going to have 4, 1, -1, and 2. And then we are going to be finding the eigenvalues and eigenvectors of this matrix here, and then using that to construct our eigenspaces. So let's first solve for eigenvalues. So let's just go on over here. We first want to take A minus lambda I, and that is going to be equal to 4, -1, 1, 2, minus our 2 by 2 matrix with lambda down the diagonal and zeros everywhere else. And we're going to know that A minus lambda I is going to be equal to 4 minus lambda, 1 minus 0, and then -1 minus 0, and then 2 minus lambda. And now we're going to want to take the determinant of this matrix and set it equal to 0. So we want the determinant of A minus lambda I to be equal to 0. So what's the determinant? If we take the determinant of this, we're going to have 4 minus lambda times 2 minus lambda, multiplying down the diagonal going from left to right. Then we're going to subtract the product of the diagonal going from right to left. So 1 times -1, let that equal to 0. So we're going to have 8, 2 times 4, and then minus 6 lambda, which is 4 times negative lambda, so -4 lambda minus 2 lambda, plus lambda squared, minus 1 times -1, which is going to be plus 1, equals 0. So we see lambda squared minus 6 lambda plus 9 is equal to 0, and then we see lambda minus 3 times lambda minus 3 is equal to 0. Okay. We can simplify this one step further and see lambda minus 3 squared is equal to 0. Okay, hold up, something crazy happened. We've never had this, so that we have more than a power of 1 on any factor corresponding to an eigenvalue. So this actually here, we have a special name for it, and that is called our algebraic multiplicity. So the power on the factor corresponding to each eigenvalue is the algebraic multiplicity of that eigenvalue. So we're going to have lambda 1, 2, and that is going to be equal to 3, because we have this occurring twice, so we have 2, 1, 2. The algebraic multiplicity means that the algebraic multiplicity of this 3, when we solve this algebraically, is the number of times that that factor shows up. So it appears twice. So algebraic multiplicity of 3 is 2. Okay. So now we have our eigenvalue. Now let's see what corresponding eigenvector we can come up with. So if we come over here, we're going to be dealing with our eigenvalue lambda 1, 2 is equal to 3. So now we want to plug in 3 into this equation here. So I'll have A minus 3I is going to be equal to 4 minus 3 is 1, and then 1, -1, and then 2 minus 3 is -1. And then we want to find the null space of this matrix. So we're going to solve this equation. So once again, we're just going to augment this one. We're going to have 1, 1, -1, -1, augmented with our 0, 0. And then it's easy to see our one row operation is going to be row 1 plus row 2 is our new row 1. And we will have this matrix. Okay, so now from here we see that x1 plus x2 is equal to 0. So then we know that x1 is equal to -x2. So our eigenvector corresponding to our eigenvalue of 3 is going to be equal to x1, x2, which is equal to negative x2, because x1 is equal to negative x2, and we have an x2 here. And we always want to write it in terms of our free variable, so we'll have x2 times negative 1, 1. So this here is our eigenvector. So now we have our eigenvector. What can we do with it? We can actually construct our eigenspace here from this eigenvalue. We're going to have the subscripts 1, 2, knowing that it's going with this eigenvalue of 3 and this eigenvector of negative 1, 1. And that's going to be the span of this eigenvector. So this means that if we consider this on a line, all vectors on this line that negative 1, 1 lies on, this vector lies on, is going to be an eigenvector for this system of A. So this is going to be our geometric multiplicity. So we think about it geometrically, it's one-dimensional, it's a line where all of our solutions are on, so our geometric multiplicity is 1. So we have an algebraic multiplicity of 2, and we have a geometric multiplicity of 1 for this eigenvalue of 3. So we can kind of draw the conclusion here that our geometric multiplicity is always less than or equal to our algebraic multiplicity. So let's look at an example of a 3 by 3. Okay, so now for our next example, we're looking at this 3 by 3 matrix. And first of all, to find our eigenspaces, we need to have eigenvalues and eigenvectors. So let's solve for eigenvalues of this matrix A. So we know that we're going to be taking A minus lambda I. So we'll have our A minus the 3 by 3 matrix with lambda down the diagonals and zeros everywhere else. So we know that A minus lambda I is going to be equal to negative 3 minus lambda, negative 2 minus 0, 1 minus 0, 2 minus 0, 2 minus lambda, negative 2 minus 0, and then 0 minus 0, 0 minus 0, and negative 2 minus lambda. Okay? And then we know we're going through the basic steps again of finding our eigenvalues and eigenvectors. So we'll take the determinant of A minus lambda I, set that equal to 0. So what is the determinant of this matrix? Okay, looks a little wild. So take a deep breath. We have as our last row here a 2 zeros and one expression. So that would be a good place to do a covector expansion. So I'm just going to go ahead and do that. Okay, so once we have done all of our algebra to solve for our lambda, we can now see that we have an algebraic multiplicity of 2 on our eigenvalue of negative 2. So we'll just denote that lambda 1, 2 is equal to negative 2. And then we know that our lambda 3 is equal to 1. So our algebraic multiplicity of our lambda 1, 2 is equal to 2. And then our algebraic multiplicity of lambda 3 equals 1 is just 1, because we only have a 1 as our power of our product, or of our factor relating to our lambda 3 equals 1. 100 times, seeing our algebraic multiplicity of 1 eigenvectors, we know that our algebraic multiplicity always has to be larger than or equal to our geometric multiplicity. So just to keep things interesting about our eigenspaces, let's look at the eigenspace created from the eigenvectors corresponding to the eigenvalue lambda 1, 2 equals negative 2. So let's just do that right on over here. So we are going to be considering lambda 1, 2 equals negative 2. Okay, from here we're going to be taking a minus negative 2 times I, which is going to be equal to A plus 2I. Okay? So we're going to be adding 2 to everything along this diagonal. And then we're going to be solving for that null space. So let's just form this matrix here. And we're going to have negative 3 plus 2 is negative 1. Negative 2 plus 0 is negative 2, 1 plus 0 is 1, 2 plus 0 is 2, 2 plus 2 is going to be a 4, and then negative 2 plus 0 is just negative 2, then 0 plus 0 is 0, 0 plus 0 is 0, and then negative 2 plus 2 is going to be 0. And then once again, we are going to be solving for the null space, so we have this equation. And then we can augment this matrix with this one. Okay, so now to solve, to see what our x, y, and z are going to be, we'll use row operations. So we'll just do that real quick. Okay, so now that we are in our reduced row echelon form, we can see that we have 2 free variables and 1 pivot variable. So we know that x1 plus 2x2 minus or plus negative x3 is equal to 0. So then we know that x1 is equal to negative 2x2 plus x3. So then if we want to write our eigenvector corresponding to our eigenvalue of negative 2, we are going to have our v sub 1, 2 is equal to x1, x2, x3, which we know x1 is equal to negative 2x2 plus x3, and x2 is equal to x2, and x3 is equal to x3. So then we can see that we have, pull out our first free variable, and we have negative 2 x2's in our first entry, 1 in our second, and 0 in our last, plus we have x3 times our this new vector, so we'll have 1 x3 in our first entry, 0 in our second entry, and 1 in our last entry. So we know that our eigenvector here corresponding to negative 2 is a linear combination of this vector and this vector. So when we want to create our eigenspace here, what we can do is we can take, let's write it right on up here, front and center, because this is the star of today's show. So our E corresponding to our eigenvalue of 1, 2, which is negative 2, is going to be equal to the span of these 2 vectors. So from this span, we can see it that anything along the plane created by these 2 vectors is going to be an eigenvector. So you can take any linear combination of these 2 vectors, which is what our span is, and that's going to be an eigenvector of A. Wow, mind blown, right? Like, this is incredible. So our span of these 2 is going to have a dimension of 2, because the basis for this eigenspace has 2 vectors, so it has dimension 2. So this is our geometric multiplicity. And if you think about this geometrically, we have a plane as our solution space, which is 2-dimensional, so that means we have a geometric multiplicity of 2. So in this case, we had for our eigenvalue of negative 2, an algebraic multiplicity of 2, and a geometric multiplicity of 2. So we can then confirm that yes, indeed, our geometric multiplicity always is less than or equal to our algebraic multiplicity. So this has been eigenspaces. We have contained them. We have found some really cool subsets of our vector space, and I really want you to go blow your own mind and your friends' minds by taking some linear combinations of these 2 eigenvectors and show that they are eigenvectors of this linear system. So go have fun.